Hi everyone, welcome to my presentation for AVS 2020. Today, the topic of my presentation is deep learning based eco-driving for connected and automated vehicles. I'm Peng. I'm a research faculty from a Center for Environmental Research and Technology, UC Riverside. So this presentation includes several research topics and papers from myself, my colleagues, and my students. So to begin with, I would like to introduce some background information related to connected eco-driving. So first, as we know, like transportation is one of the most energy-consuming activities in the US today. So according to the survey from 2019, about 28% of the total energy consumption is for people and goods-related movements. So in order to solve the energy issues in today's transportation system, connected and automated vehicles emerge as one of the most efficient and innovative solutions. So for connected vehicles, they are able to cooperate vehicles and vehicle with infrastructures. So to improve the traffic mobility and reduce the energy consumption in those selected scenarios. And for autonomous vehicles, since they are equipped with advanced sensors, so they are able to recognize the surrounding traffic environment to guarantee safety. And on the other hand, since they are able to perfectly perform the actions that we would like them to do, so if we design the energy efficient maneuvers for the vehicles, they are able to precisely follow those strategies by fully or partial automations. So by fusing the connected vehicles and automated vehicles, we're able to achieve the maximum benefit from connected eco-driving. So in today's presentation, I would like to focus on the signalized intersection as it combines several critical factors in the CAV technology, such as it have a mixed traffic with different type of vehicles, then they have relatively congested traffic, and also they have signals, which is operated by the city. So the different factors would improve the difficulty in analyzing the system, and also it brings up a very interesting topic to see how the connected eco-driving would perform in those complicated scenarios. To discuss the connected eco-driving systems, first, I would like to give a simple example at real signalized intersections in the city of Riverside. As shown in this figure, there are many components for this system. So first, the host vehicles is at the top right corners, and the onboard sensors from the host vehicle can report the sensing information directly to the vehicles, like the traffic state or the vehicle state of the preceding traffic. And also the vehicle can directly receive the vehicle and powertrain information like the speed, the RPM, and the fuel consumption rate directly via canvas. So besides these two types of local information, the host CAV can also receive the traffic and signal information remotely. So the traffic data here includes the loop detector data, the infrastructure radar data, or the other CAV's data transmitted by BSM, the basic safety method. The signal data are usually in the form of the SPAN message, the signal phase and timing message, including the current state of the cycle, and also the phase duration and the time in the current phase and remaining time of the phase. So the traffic data and signal data can be transmitted to the host vehicle remotely via either DSRC communication or 4G, 5G, the cellular-based communications. So based on the components that we defined in the previous page, we're able to show the goal of connected eco-driving. So simply put, like instinctively, the goal of connected eco-driving can be like to minimize the energy consumption while guaranteeing the mobility and safety goals. However, this definition is not very mathematical. So in order to give a more formal definition to support modeling, here we propose this kind of a formal definition. So based on the observed information, we would like to find the optimal valid action that minimizes the expected total energy consumption or other objectives over the rest of the trip. So I would like to explain some of the keywords in this definition. The first is the observed information. That means for your CAVs, even when you equip a lot of sensors, the information that you have are limited by the range of sensing and the availability of those like remote ways. So your observed information is always partial information from the environment. For a valid action, it means the potential acceleration or deceleration that your vehicle can reach in the next time step. It's usually limited by the self-vehicle's dynamics and also the preceding vehicle state and also the rules from the traffic from the signals. Third one is expected total energy consumption. It means the goal of connected driving is not to minimize the energy consumption of the next time step or next several time steps. It have a long-term goal. So you have to kind of enumerate all possible scenarios given current information and to do some prediction so that to give your connected eco driving some smart to do those like a future prediction. And besides energy consumption goals, sometimes we have some other objectives, such as the time. And for hybrid vehicle, we need to kind of have a trade-off of fuel and battery cost. So the objectives can be a kind of a combination of the different goals here. And the last term is trip. So although usually we think trip is kind of a trip from your home to your workplace, it's like a long trip. But for the connected eco driving, sometimes we don't need to plan for that long. So here we define the trip as a distance from your current location to the next good checkpoint to calculate the objective values. So the trip can be defined as your current location to the downstream of the intersection or to the end of the corridor. So, but you have to make sure your checkpoint can kind of clean the state and start another planning after it. So here are some existing research. So those research are not all the research related to connected eco driving, but I just select those ones that define a novel methodology on eco driving. So other research may more related to the kind of like field implementation or simulation tests. So I do not include everything here. So as shown in the second column, you can see existing research can be categorized into three types. The first one is a rule-based method. So usually the rule-based method is simple to implement and also need less time to compute. So it's more like computational efficient. However, the rule-based model is usually designed based on the experience of the researchers or some common knowledge. So usually cannot guarantee that the strategy that you selected is the best among all the possible strategies. So next one is the optimization-based method. So compared with the rule-based one, the optimization-based method can define the objectives and try to let the vehicle to search for the optimal goal, like to minimize the energy consumption. So mathematically, it's better than rule-based model. However, for many optimization-based model, they need a longer time to compute, and even than the time in the real time, in the real world. So yeah, it is one of the disadvantages of the optimization-based method. And also for optimization, sometimes you need some strong assumptions to constrain your model to a more like ideal case. So that means some uncertain factors such as uncertainty from the traffic, uncertainty from the actual signals can kind of be underrated in those optimization-based methods. And the third one is the learning-based method, so which is shown in the last line in this table. So in this method, we propose a reinforcement learning-based framework and combined with Unity simulations. So also for some optimization method, as shown in the line on top of that, we can use some learning-based modules to enrich the model, but still the entire framework is developed based on optimization. So in this presentation, I would like to emphasize on these two models. One is optimization, but with some learning-based modules, and the other is more like a reinforcement learning-based framework. So here is the first one, the graph-based model. In this model, we use a graph as a core for optimization, and we have other modules to support the graph-based trajectory planning. So in the figures on the left, we show the formulation of this graph. We have nodes to represent the state of the vehicles, including the speed, the distance to intersection, and time. And we use the edge to represent the optimal action for each node. And we have the weight of the edge to represent the cost in this transition. Usually it is just the energy consumption rate from one state to another. So based on this graph, we're able to achieve trajectory planning with the help of other modules. For example, on the top of the right figure, it is an information acquirement module, which gets the traffic information and signal information from outside. And those information are integrated in the information integration model and scenario identification model to finally identify the target state and other constraints from the leading vehicles and from the signals. Then the current state and target state information are loaded into the trajectory planning to finally find the optimal path to link these two. And in this model, we also have the cost function derived from the real powertrain of the vehicles. So here are some key components in this connected eco-driving system. As I mentioned, it's a modular design, so we can replace the factors in each component by others to get another variation. For example, for signal timing, if we have a fixed timing signal, it's one version, and if we replace it with the actuated signals, it's another version. Also, same for facilities, we can include the road grade and bus information. And for vehicles, we can have different versions based on the type of vehicle, like the light duty, medium duty, and heavy duty, and the powertrain, like the ICE, the EV, and the plug-in hybrid. In terms of planning scale, it can be either single intersection or corridor-based or the route-based. And for traffic sensing, it can be radar, can be camera, or can be the BSM message from other CAVs. And also computation efficiency, we have different versions. The original one is shortest path, which is time consuming. So we replace it with this one we show in the previous page. It's a solution graph, which only shows the optimal solution as the edge, which is much faster. Then we can further improve the computation efficiency and the size using some regression model, using the machine learning method. I will show in the next slides. So here we have 3 examples to replace the modules by a learning-based one. So one is for signal timing for actuated signals. The other is a traffic sensing, that we use historical traffic data to support traffic sensing. And the third one is a computation efficiency one. So look at this framework. Since we can replace each component easily by others, and we can do training just inside each module, so it's easier for the field implementation because usually we cannot get too many training data from the field. Then we show those 3 learning-based modules. One is for the actuated signals. Since for actuated signals, there are a lot of uncertainty. For example, the SPAD message provides a mean and max time to change, but we don't know what is the real time to change for the vehicles. That's why we need to use those like a historical stat as a training data, and we use those like a current stat as the input, and we use the predictive time to change as the output, and load them into this long short-term memory model to give the prediction. So based on this prediction, we're able to better give the estimate of the future signal timing data to support connected vehicle driving. The second one is a speed forecasting. So usually when you are follow other vehicles, you don't know what the vehicle is going to do. So we use the historical data in the past 3 seconds as input, and the future 3 seconds speed prediction as output to give better forecasting of the leading vehicles. And that forecasting can support Q prediction for the intersection and further support eco-driving. So the table on the right shows the RBF-based neural network outperforms the MLP-based neural network and the Gaussian method. The third one is machine learning-based trajectory planning algorithm. So as I mentioned, sometimes we need some regression model to further reduce the computation time. So this like a machine learning-based model is a good example to approximate solution in the graphics model while achieving real-time solutions and the continuity in the solution space. So the figure here shows how we replace the original graph-based model with this machine learning-based model. Basically, we have a solution table, and we train the model using the results from the solution table. And we test different methods and find that the random forest outperforms other machine learning methods in terms of the regression accuracy. For the deep learning-based approach, we developed hybrid reinforcement learning method for multi-sensor-based connected eco-driving at signalized intersections. One major challenge to solve the eco-driving problems using RL algorithms is how to handle 3 different logical tasks in the same problems. The first is energy efficiency, which requires a vehicle to drive through the intersections with minimum energy consumption. The second is intersection interaction and signal interactions. And third one is a traffic interaction, which requires a vehicle to interact with other vehicles safely. In this problem, RL framework is established based on Markov decision process. This is a mathematical framework for decision-making via the interaction between a learning agent and its environment in terms of state, actions, and rewards. In this research, the agent is defined as an eco-vehicle mounted with sensors and communication devices, so it can perceive the environment via the camera, radar, and SPAD data. The environment means the traffic environment include different type of vehicles as shown in this table. The policy here is a proposed eco-driving policy. The action rewards include both short-term benefit, like the speed and energy of taking this certain action, and the long-term benefit from the entire journey. After comparison with different type of structures, we found dueling DQN is the best among all the neural networks for this problem. The DeepQ network is a typical deep RL algorithms that use a deep neural network to predict the value function of each discrete action. And dueling DQN is applied in this research as a basic RL algorithm of this hybrid RL framework. Dueling DQN has 2 streams to estimate separately. One is for state value, and the other is the advantage for each action. So in this proposed system, we mainly have 4 types of devices. One is the onboard computer, one is radar, and then the camera, and also the traffic lights. So the brain is the onboard computer, so it will perceive the data and process the data. And it will return the longitudinal acceleration and target lane information to the vehicle control centers. And for radar, we mount front distance radar and left and right radar to detect vehicles' surroundings. And the onboard camera is installed in the front of the vehicles to detect the traffic in front. And the camera information will be sent to the onboard computer, which is a key part for the traffic perception. And also, the SPAD messages are transmitted through the traffic controllers, including the current phase and the duration time. For the decision manager, it is a rule-based model that gives the vehicle the first decisions to select different strategies. So in the decision manager, you can see the driving process is divided into different running situations according to the immediate situation of vehicles and traffic lights. The situations include the HRL-based eco-driving, the car following using IDM method, and also the stop at the stop line, and finally the emergency braking. So in this model, we use a long short-term reward functions, which not only consider the instant variables such as speed, lane change, and instant energy consumptions, but also includes some journey-based, long-term based indicators. These two types of conflicting factors in these issues are the short-term reward from the instant speed and energy consumption, and the long-term reward from total travel time and total energy consumption. So in this page, we show the structure of the deep neural network. The main purpose of the deep neural network is mapping the current observation state to the best action value in action space. So the main structure can be divided into two components. One is the hidden feature extraction network, and the two is the policy network, which applies during DQN. This figure illustrates the architecture of the proposed deep neural network. In order to extract features from these different types of data, we design a multi-channel feature extraction network, which consists of different kinds of parallel neural networks. For the image flow input, a CNN stream is designed to extract vision-based input data. On the other hand, the radar, OBD, and V2I information, we call them logical data, are integrated into a 13-dimension vectors. For the logical data feature extraction, LSTM is applied in our deep RL network, as it is powerful in dealing with those temporal data series. After getting the CNN and LSTM, the two stream features are combined through a concatenate layer, and then a dense layer-based policy network is designed by applying dual QN. In order to train the proposed model and evaluate its performance, a simulator has been constructed in this research by utilizing Unity and Unity machine learning agents. The main reason to use Unity to build a simulator is that Unity can provide a virtual reality environment in which the simulated camera can be applied. In addition, Unity ML agents provide a machine learning development platform, so the machine learning algorithms can be constructed conveniently. In this slide, we show the image of the Unity simulator, one intersection with mixed traffic. As discussed in the previous section, the scenario is built as a one-direction intersection with 5 lanes. So there are 5 different kinds of human-driven vehicles. The length of the research area is 550 meters, 500 meters upstream of the intersections, and 550 meters after the stop line. Here we show a video, which is a simulation view of the Unity simulator. So in the simulation, we have 6 different entry time in the cycle as tested, from second 0 of the cycle to second 50, which 10 seconds as an increment. So in this case, you can see the CAV may not achieve the highest speed in some situation, as shown in this video, because our HRL model learns that in such a situation, a lower speed can gain more energy benefit in the long run. For example, the vehicle can wait for the end of the red light so that eagle vehicle can pass without stops. And besides the proposed hybrid RL vehicle, we also define two types of baseline vehicles for comparison. One is called IDM, the Intelligent Driver Model, which means the host vehicle acts like a conventional vehicle controlled by IDM algorithm. The other is called Speed First Method, SF method. So the vehicle only considers the speed efficiency in the reward function without any energy-related concern. So in the following slides, I will show the comparison results between these three types of vehicles. So here is a training result between the HRL and the speed first method. So these four figures show the difference of these two methods, including the average energy consumption, the green pass reward, average speed, and average lane change number in a single journey. The IDM method is not compared here because that one is a rule-based model, do not need any reinforcement learning. So the left top figure shows that energy consumption for HRL method is decreasing via the iteration of the training, while the energy consumption of the SF is increasing, as the SF method is trying to get higher instant speed without considering the energy consumptions. The right top figure shows that the HRL method is learning more about how to interact with the traffic light intelligently, because the average green pass reward increases in terms of iteration. On the bottom, we show two figures to compare the mobility benefit of both HRL and speed first method. It shows that actually both methods have very similar performance, and the performance usually better than the IDM method. So now it's a test result. So in the test result, we use red, purple, and blue lines to represent the speed profiles of the HRL method, IDM method, and SF method, respectively. The y-axis here shows the instant speed, and x-axis shows the distance. So the title of each subfigure represents the initial travel time, like phase time, and the entry speed of the host vehicle. From these figures, one can first observe that the acceleration value of HRL is obviously slower than either IDM or SF in almost all scenarios. That means HRL can avoid some unnecessary speed drops or stops, as shown in those figures that I highlighted. And on the other hand, HRL model can better interact with mixed traffic by smart lane changing, which have both mobility benefit and energy benefit. So in general, HRL can drive in a more efficient way than IDM and SF method. Here we group the test result by different entry speed. So you can see 10 km per hour and 20 here. And in the next slides are 30 and 40 km per hour entry speed. So besides the mobility or the trajectory difference, we can also see the energy saving of the HRL method. So based on the statistics, the average energy saving from the IDM method is 12%, and the energy saving from the speed first method is as high as 47%. So it means the HRL method have a very significant performance in energy. Besides the connected vehicle driving at signalized intersections, we also have some other research at other type of roads facilities, such as the freeway segments. So here we developed the vision-based eco-ACC algorithm for the traffic along the freeway segments. So here are the conclusions. In this presentation, we've shown two types of method. One is an optimization-based method plus some learning-based modules. So we think this method is good for good implementation at the early stage of the CAV deployment. And the second approach is a deep learning-based approach for connected eco-driving. So we found that by the hybrid reinforcement learning, the proposed method can achieve good mobility benefit while gain very good energy benefit. So in the future, we would like to test more vehicle and powertrain combination and test more like a corridor-based simulation and network-based traffic. Also, we would like to investigate those cooperative vehicle driving strategies, such as vehicle cooperation and vehicle signal optimization. So thank you for listening. So that is the major content of my presentation. So if you have questions or comments, please come to my session in AVS, and also you can send an email to me. Thank you.